Well, welcome back, folks. Looks like we can get started, and congratulations again getting through our second exam. I've emailed everyone's grade exams back, but I haven't released the solutions just yet. I did have a couple people with valid medical reasons to take the exam later in the week. So I'll hold off on posting the solutions, but I'll get them posted towards the end of this week. So with where we're at so far, we finished the section on the chain rule. We didn't do the very last application, but for the sake of time, we're moving forward to section 3.6. And in the 3.5 homework, there isn't no crazy application at the very end. That one was more just a preview of applications if we had available time. Then after we finish section 3.6, either today or very early on Wednesday when we come back, we'll be moving into section 3.7. So that's the last one of chapter 3. Well, any questions at all, folks, before we get started today? Okay, looks like it's a small class today, but hopefully people join in as we get going. If it's just going to be us, though, we'll make it work. There's no quiz due this particular Wednesday. Thanks for asking about that, Emily. And the only reason there's no quiz is because of this being an exam week. I felt like it was busy enough as it is, so we didn't post any new quiz on that particular week. But we are going to post a new one on this current week, which will be due the next week. And I'm thinking what I'm mostly going to go for our quiz number, which is it up to? I think it's 6. Yeah. For quiz number 6, it's pretty much going to be a problem right out of this section right here, 3.6. Other questions at the moment? Okay, well, let's get going. In section 3.6, this is one of our bigger application sections before we get into the entire chapter on applications of the derivative, chapter 4. And this one's kind of a nice one in the sense that it's not anything totally unfamiliar. If you take pre-calculus, you probably looked at the exponential growth and decay model, this one right here by Theorem 2. So really all that's going on in these notes is instead of just talking about this model like you would in a college algebra or a pre-calculus class, we're saying where it came from. It came from this right here, the differential equation. So here's where we're going to start on the notes for this section. It says y of t is the value of a quantity at time t. This could be a quantity of bacteria in a petri dish culture. It could be the population size of a country or a county or a city, or it could be the amount of mass in a container that might be unstable, so it's decaying exponentially. So anything along those lines is the quantity at time t. We don't always use y of t. Sometimes we use p if we're talking about a population, people or bacteria, for example. And sometimes we use lowercase m if we're talking about the mass of a radioactive substance. But generically, if we're not sure in the context, we just call it y of t. So y of t is the value of some quantity at time t. Imagine something either growing or shrinking. It goes on to say, if the rate of change of y, let's hang on right here on this statement. When it says the rate of change of y, one thing that we need to practice is they're talking about a derivative right at that statement. So the rate of change of y is this portion right here of the equation. So I go on to say, if the rate of change of y with respect to t, so that's a derivative of y with respect to t, I guess we can highlight that whole thing in yellow. So all that is indicating the derivative. If the derivative is proportional to its size y of t at any time t, let's take this portion right here. Let's see what they're saying about this. Something being proportional to its size y of t means you take some constant, say k, multiplied by y. So that's our proportionality constant k. Let's call this k is the constant of proportionality. Kind of a long word, and it goes right here. So if it's proportional to its size y of t, we take that proportionality constant k and multiply by y once again. But k is pretty special as a as a constant in this context. If, for example, K is positive, we have relative growth rate. If K is negative, we have the relative decay rate. And the whole formula right here turns into the law of natural growth for positive value of K, or the law of natural decay for negative values of K. So whatever K turns into, that's the quantity that's going to tell us if we're growing exponentially or if it's decaying exponentially. Well, any questions, folks, with the equation right here? Okay, well, it's really a new kind of equation when you think about this. It's an equation because there's equality in the middle, but what makes it special is there's a derivative right here in this equation. That means we call it a differential equation. And when it comes to finding a differential equation, the solution is not necessarily a number any longer. It's going to be an entire function. So theorem 2 is telling us for the differential equation up here, the only solutions have this format: y at a value of 0 times e to the power of kt. And notice k just comes up again and again in these kinds of problems. So here's k and y of 0. So these notes are kind of tricky in a certain sense. Sometimes we're using the solution to the differential equation right here in theorem 2 by the red dot. But if the question says anything about a growth rate or a decay rate, then we have to know we're using the differential equation right up here. But this is our write-up so far. And I'd say out of all this information, the new content is this, with that fact that we're talking about the derivative, not just the solutions. Well, example 1 is kind of a gentle example where we're just breaking down this model here by theorem 2 and see what the moving parts are. But any questions or comments at the moment with the first part of the notes? Just moving the windows a touch, there we go. Okay, let's keep on going then. So with all this write-up, here's where our model looks like on this one. Just a random example. Looks like it's the population size of a country at time t is what the write-up says. But our purpose with this one is just to find out what all the moving parts are for a model like this one. We want to know which portion of the function represents the relative growth rate, for example. Relative growth rate is going to be a value k. Anyone see what the value should be right here for k, given that model here? Oh, looks like the chat has a pretty much a tie, it looks like. Both Dana and Emily say 0.235, good call. So the trick to this is if they just give you the model straight out like this one, the relative growth rate is going to be the value that's multiplying t right here in the exponent. So it takes on this value right here, 0.235. There's the eraser. So 0.235 goes here. And notice that is a positive quantity. That means we're really talking about the law of natural growth, k bigger than 0. So we really do have a growth rate. If this came out at negative, then nothing would have made sense in part A. We would have had to say the decay rate instead of growth rate. So that's one down. Next part of the function we need to think about is the initial population size. But I guess I kind of gave away the question by the color coding. The initial population size is this value right here, right before you multiply the base e exponential. So in this problem, it's going to be 750. A different way to think about this is when it says initial, it means you're taking the model population at time t and putting in 0. So the 0 here comes from the word that says initial. And we can evaluate this at 0. All we're going to do is go right by where the red dot is, plug a 0 right in that position. So even if we didn't know it was 750, we could kind of just follow our nose, plug 0 into the function, get 750 e to the power of 0.235. Then next, with the parentheses of 0 or times 0, that's where the 0 got inputted into the function here. So now we have 750 multiplying e to the power of 0. E to the power of 0 is a 1, so this is just 750. And the unit on this would be, I guess, people, since it's a population size of a country. So that's the initial population size. It's kind of convenient. It's just right there, multiplying the base e exponential. The growth or decay rate is going to be in the power position, whatever the constant is, that's multiplying the variable t. Well, any questions at all, folks? Looking at those two key parts of the model, the initial size and the growth rate? Okay, next, part C is a little bit tricky in a certain sense. It says, show that the derivative of p with respect to t, so you could think p prime, is really equal to k times p, the growth rate times the population at time t. Well, we have the function p of t right here. And essentially what this part C is saying is, show that right there really solves the differential equation. So that's what we're trying to show on our last part, part C. Which is a worthy thing to do in a class like this, because unless we talk about the derivative, there's no calculus at all in this problem. And so this is what makes it a question that belongs to our class right here, talking about the derivative in part C. So here's how this work is going to go. Start by just grabbing the function. It's this one here, not the one in the theorem. We're using p instead of y because of the context, the population size. So we just take this and differentiate it. So let's start by writing out dp dt. That means we're taking the derivative of p with respect to t, or we could just say p prime if you prefer. Usually Leibniz notation is more emphasized in an applied setting like this one, so I'll often use the Leibniz notation in this situation. So if we're taking the derivative with respect to time, we come over here, and first thing we use is the constant multiple rule. It tells us 750 is unaffected, so it's just going to be 750 multiplied by the derivative of e to the power 0.235t. I'll put a little prime symbol there to say we're differentiating that part. We'll take our time with this one because anything that's an actual applied problem, I feel like it's always a trickier derivative. So only thing we did here is the constant multiple rule. Next thing we have to do is differentiate that function. Now, if it looked like this, that's a wonderful derivative. You would just say y prime is itself e to the t. It doesn't work on this one. This one turns into a chain rule problem, all because of the fact it's not just a t in the exponent. We have a function of t, a linear function. So this right here is the derivative we'll handle second, the inner function. So this is the breakdown anytime we're using a chain rule process. The outer function is the base e exponential. Let me write out this way just to be more specific. I think chain rule with an exponential is kind of harder to visualize. So I'll just spell it out right here. E to the x is the outer function, which we have to handle its derivative first. And so this whole process will be chain rule. Okay, so there's our setup right before we go to actually compute the chain rule over here. Any questions at all, folks, with the setup? Okay, so let's go over here. First, we're copying the 750. Next, the initial analysis that we jotted down here, we're just going to follow it to the letter. So step one, differentiate e to the power of x. It would look like this. Oh, and I said that in a weird way. E to the power of x is not exactly what we're looking at. Let me fix this a little bit. It should be e to the power of t, since the input variable is t, not x. That's a mistake I make constantly if I don't think about it really carefully. Let me highlight that in yellow just to show that mistake. So starting over, the derivative of e to the power of t is e to the power of t, but we're doing a chain rule process, so where the variable t goes, we'll just put in a placeholder like that. Then the chain rule says we multiply it by the derivative of whatever went into the first placeholder. So if we can tell what goes right here, we're essentially in business. We can finish out the chain rule really, really fast. But every single time we do this, the thing that goes in this position is the inner function again. So 0.235 goes here. 0.235t, that is, don't forget the variable. At this stage, the parentheses are not needed. We can drop them on the next step. We only plug them in there just to help visualize this derivative. Then in the second placeholder, we put in the same exact function, 0.235t. Like this multiplication dot is just more confusing than necessary. Let me take it off. So next thing we need to do is just compute that derivative. Well, that's a degree 1 polynomial in the variable t. So when we differentiate that by the red dot, we just get the constant, 0.235. So this turns into 0.235. I'm going to put the constant way in front. So after taking that derivative, the rest of this right here is just copied in. So let's copy that in, 750 e to the power 0.235t. So another way to think about this is when you go to differentiate that function, you get the same exact thing back, but then you multiply by the derivative of the exponent, 0.235t, and that's where this 0.235 came in. Well, we've got it, folks. That's our derivative. And hang on, I'm having some technology struggles. Sometimes things are easy to delete, like the highlighting. Other times, Microsoft just wants to fight about it, I think. There we go. Well, any questions, folks, to get to that stage there? Okay, well, let's look at this even more closely. There's a couple substitutions we can make. For example, notice the 0.235, it just came right back. So K actually goes here when we make a substitution. And for an even bigger substitution, take a look at the 750 e to the 0.35t. That whole thing, that's just p of t coming right back. So we can say that this derivative is equal to K, that's the 0.235 times the population size at time t. So what we've said in essence is that from this part, that's the derivative of the population size with respect to time. And from this part, we just said it's proportional, there's the constant of proportionality, to its population size. So at any time t, the rate at which it grows is proportional to its own population size. So let's make an overall statement. All this work here implies that the derivative of p with respect to time is equal to kp. And that's what we were meant to show. The derivative of p is equal to k times p. Notice we don't put p of t right here in the red dot, but that's more of just a stylistic choice with differential equations. If you did say p of t right here, no harm done. Well, we did it, folks. This is the rundown of dealing with this thing, which is the solution to that differential equation. So in other words, in example 1, we have this right here is the differential equation. Theorem 2 provides this function model as a solution. And we just checked for this one specific example, this model right here, population 1, that sure enough, if you differentiate it, you get that as a result. That means for the notes going forward, we will always take dp dt equals kp, or granted. What I mean by taking that for granted is that's a formula you never have to derive again. We did it just once just to show how it goes, but from here on out, we'll just use that formula every time it comes up instead of actually cranking out the derivative like we did here. So that's our rundown on how these kinds of models work. And down below is just 3 common examples like you'll see in the homework for different situations of either exponential growth or exponential decay. So I think we're about ready to start off our first problem, example 2. Any questions whatsoever with what we did so far before we get started? Okay, well, let's begin then. So here's our new content. We are told a bacteria culture grows at a constant relative growth rate. The moment it says this right here, I was meaning to highlight that. Let me try again. The moment it says that information right there, that means the population size at time t is now equal to p at 0 times e to the power kt. So from here, we obtain that model. They also give us more follow-up information. These are initial values. The bacteria count was 600 initially. The word initially right here is super important. For a lot of these problems, we have to read what they're trying to say through the context. But if it says initially, that means the population size at time 0 is 600. And I want to target that arrow there just a little bit better. From the word initially, we plug in 0 into the model and get 600. And all part A is asking us to do is find the expression for the number of bacteria at t hours. That's the right expression, but there are 2 unknowns. We need the initial value. We found it just by reading the problem and understanding the context. We also need to get the value of k. So let's keep on going. In stages, our model is now population size at time t equals the initial population, the problem said was 600 bacteria, times e to the power kt. So the moment we solve for k, our work is complete on part A. Just want to fix that color coding a bit. So there's our brand new model. Let's see, we got up to this part of the reading. Bacteria count was 600 initially and 750 after 3 hours. Let's highlight that one in green because that second piece of information is what's going to help us get the value of k, the growth rate of the model. We just have to put it into our own language. So when you see this information, I think it's maybe too many arrows for the notes. Let's take that off. When you see this information, just rewrite it in function notation. Population size at time 3 hours, so p at 3, is 75,000. So that's the next information we got from the last part of the information. And somehow, some way, that statement there will get us the value of k. Well, any questions at the moment, folks, to that stage? Okay, so the major trick at this point is we basically have the whole model. We're just trying to find out what k has to be with the given information. So when it says p of 3 at the left-hand side, what we're literally doing is coming over here and plugging in 3 for the time variable t. So the left-hand side turns into 600 e to the power of k times 3. So that's all we've have done is put in 3 for the variable t right at that step. So that takes care of the left-hand side. Right-hand side is 75,000. So the problem now devolves into just solve this exponential equation right here. That's really not too bad. It might be a bit of review if you haven't done it in a while, but it's like riding a bike. Once you see what the solution is and you apply it a few times, it becomes like second nature. The very first thing we need to do is get the exponential function completely isolated. So we need to divide both sides by 600. So let's get our trusty calculator out. And we need 75,000. Sorry about that. 600 looks like an even 125. So e to the power of 3 times k is 125. Now, once we get to this stage, this is where knowing information about logarithms is actually really helpful. The base e exponential is an invertible function. All we need at the next step is to find its inverse. And it turns out the inverse of that function is the natural logarithm. So what we do is we take the natural logarithm of the left side of the equation. We take the natural logarithm of the right side of the equation. And because these are inverse functions, whatever the base exponential has done to 3k, its input, the logarithm has totally reversed it. So in other words, that's a clean cancellation right there. And we've liberated the exponent, 3k. So 3k is now equal to the natural log of 125, which means we have the relative growth rate. All we need now to do is just divide by 3. So k is equal to the natural logarithm of 125 thirds. Well, we're just about there, folks. After solving that equation, we come back over here and just plug it into the model. So let's write this out carefully. Let's put a little therefore symbol just to say this is our conclusion with all the work we put out. The population at time t by this model would be equal to 600 times e to the power of, it's this number times t. So usually the way I'd write that out is put t in front just to visualize it a little bit better. Then where k is, we're going to read it out like this. T times the natural log, 125 divided by 3. Just making sure everything looks like it's in the exponent position, because we do have to calculate with that function there, and accidentally writing the natural log a little bit lower could actually trip us up and get really bizarre values in the calculator. So try to fit everything into the exponent position, and that's our model. Took a little bit of work to get to this stage, mainly because we had to solve this equation in the middle to get there. Any questions at all, folks, getting to this conclusion? Okay, so far in these notes, we really haven't done any, well, not in the whole notes, but so far on example 2, that's the better statement. On example 2, we really haven't done any calculus except just knowing that the fact it was talking about a derivative gave us that solution. That's the only bit of calculus. Part B requires no calculus at all either. It just wants to know the number of cells in 2 hours. The model here, P at t, is the number of cells at any amount of hours t. So we plug in 2 right into that model. And that means this next step is going to read out this way. Population size at time 2 is going to be equal to 600. E to the power, 2 goes in the variable t position, so it's going to be 2 times natural log of 125 divide by 3. Next thing we have to do is throw this into the calculator to get a result. But let's make a comment right here. Imagine you're doing this exact problem on exam 3. That's kind of stressful putting all this into the calculator in a timed exam. And so the way I grade these for partial credit purposes is that if you put this on paper, that's where your partial credit is. So even if you make a mistake on the calculator and got some weird wild number that's not even in the right ballpark, I'll say that that's wrong, but I'll look at this really, really carefully. The form is accurate right there, then you get essentially all of the credit. If this was, say, for example, a 5-point problem, even if the answer is wrong here, if this format's correct, you might just lose like a half a point and get 4.5 points out of 5 on a real exam. So let's make a statement right here. For partial credit, always show this on paper. So if you're doing a quiz problem or an exam problem, writing that down, what's about to go into your calculator, can get you potentially massive partial credit. If all I see is a number and it's not even on the right track, then I have no basis for partial credit. So that's the purpose of all those comments there. Now let's actually do it ourselves. Let's throw this into a calculator. This will do just fine. Desmos can do a whole lot more. You can plug in the whole function right here in the calculator, and then on the new line, just calculate p at 2. But that's not something that carries over to an exam situation very nicely. So I'm going to do these problems as if we were using a calculator on a real exam. So non-graphing calculator, I'll just put it into this format. So let's go left to right, 600. Then find your base E exponential, raise it to the power of 2 times, oh, that didn't work, 2 natural log, I guess I can't put a times there, or it drops me off the exponent, 125, divide by 3. Notice how this whole thing got smaller when we would divide by 3. That means all of it's being considered as an exponent. And so that means this number is something we can trust. Looks like definitely it's a rigged problem, exactly 15,000 bacteria. Well, anyone getting something slightly different in your calculators, or are we getting about that value so far? Okay, sounds like we're not having too much trouble. I sometimes think this is kind of the most frustrating part, but that's probably more about WebAssign. If we make the simplest of mistake on here, WebAssign will complain. So watch out for things about rounding errors or the amount they want you to round to. Sometimes you've done everything right, but it's just the answer you gave was rounded incorrectly. So if you try problems at WebAssign in section 3.6 and you know your answer is right, but it's not being accepted, definitely hit the Ask My Instructor button on those kinds of questions. I'll look at your answer, look at the answer it's supposed to be, and if I decide it's just a rounding error, I'll tell you what the correct answer should be so that you don't have to be bothered so much about getting the answer in perfectly. So in our problem, all we have to say is 1,500 cells, bacteria cells. So the size of the population, 2 hours into this experiment, went from 600 initially to about 15,000 cells. Makes sense for population growth. And this model probably does a really great job in describing the size of the bacteria. In the short run, after maybe, say, 36 hours, there's going to be a run out of resources. The population is not going to actually start growing. It could actually begin shrinking after some point. But in the short run, this is actually a pretty accurate model. Oh, Dana asks, how would you put that into a TI-30X2S? Thanks for asking about that, Dana. It's actually kind of tricky. But the thing I like about that calculator that you mentioned is that one particular calculator does allow you to put this all in one line. So that makes it slightly more convenient. Now, I'm going to demonstrate this with a slightly different calculator than that one. And the reason I'm using this banned calculator on exams is just to show what it would look like on the TI-30X2S. So let's give that a try. Because I've never done that before on this computer. Let's use the TI-83. Again, we can't actually use this calculator on a real exam, but just for the purpose of showing a demonstration, here's how it will go. Your readout should be very similar in the TI-30X2S, if I remember that model number correctly. We'll go like this. First, 600. Let me increase the brightness on this. And let me double check. Is this, it's kind of hard to see on my screen. Are you all able to actually see this on your screen? Okay, great to hear that. So it's going to be 600. Then on your calculator, you're looking for the natural log button. It should be about on the same side to the left. Hit probably what's a second key up here, the LN button, and you should get something about like that. E up arrow to say E to some power. Then next, we're writing out the exponent, verbatim, just going left to right. So 2, the natural log, just hit ln. 125 goes inside. But once we put in the 125, don't forget to close that parenthesis there. That's where it can get a little bit confusing. That parenthesis closed, now and only now can we do that part, division by 3. Then we opened a parenthesis here for the exponent. We should close it as well, just for the sake of safety. So we have 2 open parentheses, and then going here, there's 1 and 2 closed parentheses to match up. And you should be getting about 1,500, well, not about, exactly 1,500. So this is what it looked like inputted into a calculator. Actually, let's take a screenshot of just that much, just to show. I'm gonna kind of hide the fact that we used a bad calculator. But again, this is just about what it looks like in anybody's calculator. Let's put that right here. I guess that deserves a note. I'm gonna say, this is what your calculator should look like. Not the whole calculator, because again, this one's not allowed on exams, but just the screen. Well, any other questions, folks? Getting that out? Oh, gotcha, Dana. Yeah, that's one of the things that's easy to miss on this. The parentheses are really, really touchy for this kind of function right here. Okay, well, again, not a lot of calculus in this problem, which is weird because this is supposed to be a calculus class. There's no calculus in part B, just a function evaluation at its heart. Sure, a tricky one because of the exponent being so involved. But now on part C, this is where calculus finally enters into the problem, because they're saying, find the growth rate at 2 hours. And the moment they said growth rate, they're talking about the derivative. So this is kind of a dangerous problem in a certain sense. If you read part C in just a generic application, you would assume you have to differentiate P, that function right up there, and then plug 2 into the derivative. But actually that's not the case, because P of T came from the solution of an actual differential equation. So the moment it says growth rate, we should immediately write this. dP dt. So that's the growth rate at any time t. We want it at 2 hours. So we're going to take the derivative, evaluate it when time equals 2 hours. But let's write out the formula here on the margin, maybe to the right. dP dt is equal to k times p. So this is a given formula. That's the formula given at the start of the notes, the one we verified as true for a particular example, in example 1. And now what it means is, in part C, we don't have to calculate the derivative, we just grab it. So there it is, we give it k. That's just going to be natural log 125/3 once again. We multiply it by the population, p. But inside the population, we input 2 hours. So this is the whole answer to the problem. We just have to crank it out. Doing some substitutions. First, we can have k undone here by putting in that value, natural log 125/3. Then multiply that whole answer by population size at time 2, which was just 1,500. So let's write this all out and get, let's see, there's lots of calculators to choose from. Let's go with this one right here, maybe. This one's not as bad of a computation. So I'll go natural log 125 divide by 3, then just go over here times 1,500. And that's our value. To one decimal place, we get 24,141.6. So that's the growth rate. And In part B, the answer was just 1,500 cells. But because this is a growth rate, we get the unit by going to the numerator. P is a population size in cells. Then use the denominator unit. That's in hours. And so this whole derivative tells us that at 2 hours into the experiment, the growth rate of that bacteria is increasing by 24,141.6 cells per hour. And this growth rate absolutely is time dependent. If we put in 1 hour, we get a smaller quantity right here. We plug in, say, 5 hours, this is going to become very, very large. As time goes on, because this is growing exponentially, the growth rate just gets higher and higher and higher. So even though this problem didn't ask for units, I would encourage you to write them down anyways, because it helps us remind us, what did we even calculate? This was just the size of the population at time 2 hours, but this is how fast it was growing at time 2 hours, 24,141.6 cells per hour. So part C right there is the calculus part of the problem. Part D is going back to algebra, so it's a short part of the problem. But any questions at all, folks, getting through part C? Okay, so what we know so far is that 2 hours are up to 15,000 cells, but it's growing rapidly at time 2 hours. And now a follow-up question says, well, how long will it take to get to 200,000 cells? That's kind of hard to guess, but if I had to guess, it's got to be somewhere maybe in the 4 or 5 hour range. But this is exponential growth, so answers can be pretty surprising. Here's how we resolve a question like this one. First, let's see, I think we're going to need maybe a little bit of additional space. Let's put it down into the next page. When it says, when will the population reach 200,000? From this part, the population, we're referring to P of T once again. Reaching 200,000, it just means set it equal to 200,000. So the problem implies this equation that we have to solve. And I forgot what the model was. Let me go up here and grab it real quick. So on the left-hand side, we just substitute this entire thing, the model itself, and put in 600 e to the t times natural log 125 divided by 3 equals 200,000. So that's our first step. Well, I guess that's the second step. Step 1 is put in the equation population set to 200,000. Step 2, just make a big substitution. In place of P of T, we put it in the right-hand side, this stuff. And the last thing we're doing is actually pretty similar to what we did at the very start of this example too. We're solving for T this time is the only difference. To solve for T, we should divide out 600 on both sides. Let's see what that should come out as. So 200,000. Just double checking on my zeros. Divide by 600. Looks like it's 333.3 repeating. So we've got 333. I'll use a repeating symbol, 0.3 bar. E to the power of t, natural log, 125 thirds. So that's always our first step, solving an exponential equation. Next thing we do is eliminate the base exponential by taking the natural log of both sides. So natural log, e to the power of t, natural log 125 thirds. It's just a lot of copying is sometimes a challenge with these problems. Natural log 333.3 bar. Then again, here's the next step. Natural log and basic e exponential wipe each other out. All that's left is the exponent itself. T, natural log 125 thirds, is the natural log of 333.3 bar. And this step we took right here by the red dot is such a common step when you're dealing with these equations. that a lot of people end up getting into this habit. Going from here to here is a good shortcut. I usually show the step in the middle where the red dot is, just to show the logic of how the shortcut comes to be. We took the natural log of both sides, and so the base exponential is gone on the left, and we see the natural logarithm on the right-hand side. Any questions, folks, to that step? Okay, well, last thing to do is, to solve for t, we just multiply by the reciprocal of that fraction. So t equals, well, let me get a more official looking pen first. Okay, starting over again, t equals, we're multiplying by 3 over natural log 125, clears off the left-hand side, and moves over to this side. Multiplying natural log of 333.3 bar. And so this is the thing that we have to toss into the calculator. Let's use this calculator here, just for the sake of, this one is maybe a little bit of a nastier computation. This is what it would look like on an official calculator. So let's start off with the fraction. 3 divide by, hit the ln button and input 125. Then the next thing here is, if we just hit times right away, this calculator will interpret order of operations correctly. That this thing multiplying is going into the numerator. I would have to put extra parentheses to keep this thing in a denominator. So just go times natural log 333, that's a 33 right here. You want to put in exactly, for the 0.3 bar, just type in plus 1 divided by 3. Or you can just go point and maybe 5 or 6 threes, and that would give you a very accurate answer. So throwing that all into the calculator, you should be getting values similar to this in time. Hey, about 3.6 hours. I would have guessed 4 or 5 hours, so it reaches a population size of 200,000 very, very quickly, whatever this bacteria is. So to 2 decimal places, this would round up to 3.61 hours. Well, we did it, folks. That's the full rundown of an exponential equation like that one. Any questions at all getting through these steps? Okay, well, when it comes to exponential growth, usually the major critical step is this one right here, when we're solving for growth rate k, which is a typical thing that you have to do for these kinds of problems. But the way exponential decay problems are stated actually helps us out quite a bit on that step. There are some pretty major formulas when we're talking about exponential decay. The half-life formula, for example. So something is decaying exponentially, then the half-life is the time it takes for half of your material to have been totally gone, disintegrated or something along those lines. Half-life is denoted by the symbol lambda, and let's write that out. This symbol here is referred to the Greek letter lambda. Not sure if I'm spelling that right, but let's go with that. And lambda is going to be always equal to negative the natural log 2 divided by k. There's a little bit more to say about this formula. It's a half-life formula, and if you look at negative natural log 2, there's actually a different way you could put that number in. Negative natural log 2, by properties of logarithms, would take that negative sign and turn it into a coefficient. So it becomes natural log 2 to the power negative 1. Let's put a little arrow here just to show what happens. That arrow is not very good. Let me try it again. So with properties of exponents, we get that result, properties of logarithms. Then on the next step, with properties of exponents, this turns into the natural log 2 to the power of negative 1 is 1 over 2. So it's really kind of unfortunate in my opinion. This is how half-life formula is usually written out, negative natural log 2. But if you put natural log 1/2 into that numerator, you still have the same exact thing, but it reminds you that, yeah, that's definitely half-life for sure. But aside from complaining about this formula, notice the thing that happens to this, which is kind of a miracle. The decay rate, K, is part of this equation in the denominator. So if a problem gives you half-life, you're dealing with exponential decay, but it means solving for K is extremely rapid. In fact, this equation here by the red dot is just as good as this equation. K equals negative natural log 2 divided by the half-life lambda. Oftentimes we use this equation if we just want to build a model really fast. If we have a model but we want to know what the half-life is, then we use that equation there by the red dot. Well, either way, any questions, folks, about the half-life or the related equations? Okay, so here's how a pretty standard kind of question along those lines are going to go. We have information that the half-life of plutonium-239 is approximately 24,110 years. So this is the not great stuff. You could make some interesting missiles and things like that out of that kind of plutonium. Next, it says a shipment of 1,000 grams of this plutonium arrives at a secure location where it's to be stored indefinitely. So that's good, that kind of stuff. If we just hid it for all time is not a bad idea since this is bomb making material. I guess it could be used safely for energy production. But what we want to do with all this is find an expression for the amount of mass that remains at time t. Well, if they gave us information about half-life like we have here, then this is an exponential decay problem, and we can say m for the amount of mass of plutonium-239 at time t is going to be the initial mass, m at 0, times e to the value, or excuse me, e to the power, k times t. So this is just like example 2, where we need to find out the value for the initial mass, m at 0, and the value for k. Let's just go in stages. Anyone see in the problem what the value of m of 0 should be? I think this one's kind of tricky because the readout to the problem never says initial amount, but we have to infer that it's an initial amount. And want to see what that value ought to be? Oh, we got a chat come through. Awesome. Oh, sorry about that. It sounds like the audio had trouble. So we're trying to find out what should be the initial value in this particular problem. Anyone happen to see what the initial amount should be? M at 0? Yes, absolutely. When it said a shipment of 1,000 grams arrives at a secure location, that's when time starts. So that's going to be the initial amount at time 0, the instant it arrived wherever that location is. So this 1,000 grams right here is the initial amount, m at 0. So 1,000 grams of this not so great stuff. That means we can now update the model and say on the next step, mass at time t is equal to initial mass of 1,000 grams multiplied by e to the power of the decay rate, k, times t. So our last thing we have to do is solve for that decay rate. But this example 3 is a lot different from example 2. there's not a second equation like this one from which we can get that decay rate. But what we do have is information about the half-life. We're told the half-life of plutonium-239 is 24,110 years, and that means it goes right here for lambda. Let's write this out in stages. From that piece of information, we're given that lambda is equal to 24,110. Then we go back to this equation, the brand new one that we wrote out, and write k equals negative natural log 2 divided by 24,110. So now we have our decay rate. What makes it a decay rate is the fact that this thing is now negative altogether. So grab this, plug it in for the value of k, and we have mass at time t is the initial mass of 1,000 grams multiplied by e to the power. Let's see, we have negative, I'll put that there, and squeeze in the variable t. These are kind of touchy to write out in a way that doesn't hurt the eyes, so we'll always do our best. What I'm doing is taking the variable t and just putting it right there in the middle so it isn't too crammed as an exponent. So negative t natural log 2 divided by 24,110. That's kind of hard to on the eyes, but that's my best attempt to write it out in one line. So that's our answer of part A, our entire model. Any questions, folks, getting to that step? Okay, now that we have the model, part B is just a simple follow-up question. This is the mass at any time t, and we want to know mass at 100,000 years. But the cool thing about these problems is, I think in my opinion, if you have a half-life, sometimes it's not bad to kind of guess at these things. And guessing doesn't sound like the best mathematical technique, but sometimes it's helpful because if we do this problem as a real exam question, if you have additional time to check your answers, this is a fast one to check to see if your answer is even reasonable. So here's what I mean by that. We have an initial amount of 1,000 grams. Let's actually use this calculator right here. I think that'll be a little bit easier. So let's plug in 1,000. There we go. That's the right number of zeros. The half-life is 24,110 years, kind of an awkward number. But imagine it was exactly 25,000 years. That would mean after 100,000 years, 4 half-lives have gone by. Oh, the negative right here came from the fact that we're dealing with exponential decay. And where the negative really came from was this right here. It's solving for k, we had a negative value when we plugged in the half-life in that location. Does that help out, Kaylee, finding that negative value? Yep, you bet. Thanks for asking about that. Other questions so far? Okay, so we have 1,000 grams initially. Half-life is about 25,000 years, so we're definitely fudging it and just estimating. 100,000 years looks like 4 half-lives. So if you go divide by 2, that's 1 half-life. Let me move this over. We'd have about 5,000 grams. If we go, say, 2 to the power of 2, that's 2 half-lives. 2 to the power of 3 is 3 half-lives. And 2 to the power of 4 represents 4 half-lives. It's not quite 100,000 years, but we're getting pretty close to it. So we should be at about this amount, just a little bit less. That's not the official way to calculate. This is more just a way to see if your answer is in the right ballpark. The official way we do it is we take our model right here, and we're plugging in 100,000 years in for t. So it reads out like this. Mass at time 100,000 years, we are all long and gone after that point, but we still want to know how much mass there's remaining, is going to be 1,000 e to the power of negative. So in place of t, let me highlight this in yellow just to emphasize, We're throwing in 100,000 inside that location, so it's going to be negative 100,000 natural log 2 divide by 24,110. Kind of hard to look at, but again, for the sake of a real exam, definitely put this on paper so that way, even if there's the simplest mistake on the calculator, you'll still get massive partial credit if this is all correct right here. Now let's use this calculator just to help out with what it would look like if you're using, say, an exam to prove the calculator. So you always want to go just left to right, try to read it out verbatim. So 1,000, the basic exponential is right here to the left of the natural log key. So second ln. Now here we have to literally hit the negative sign, this one. So start with negative like that. 100,000. Okay, I think I've got the right amount of zeros. Let me just double check. Always makes me a bit paranoid. Then natural log 2, ln2. Don't forget to close that parenthesis right there. And then and only then do division 24,110. 24,110. Close that final parenthesis, and this is about the value we all should be getting. Double checking in Desmos, this is our ballpark guess, 62.5 grams. So that's more encouraging. We were expecting a little bit less because more time went by if we were just dividing by 2 to the power 4. That's not exactly 100,000 years just yet. So let's see, what are we rounding to? Nearest 10th. Well, let's just take a screenshot. That's going to help out a little bit easier, I think. So in an exam setting, this is about what it should look like in your calculator, putting it all in one line. And we get 56.4 grams. So that's how much of this material is going to be left after 100,000 years. Well, any questions, folks, with part B? Okay, well, we're at the part of the problem where finally we're doing actual calculus instead of just reviewing algebra material. When it says at what rate is the sample decaying after 100,000 years, we do this next. This one's the derivative, but we already have a formula for that derivative. dm, the rate of change of mass. dt now says with respect to time, will be evaluated when t equals 100,000 years, takes a law space just to write that out, is going to be equal to the relative decay rate k times mass at 100,000 years, which is the value we just calculated. So now plugging in value for k right here, we're throwing in that quantity, negative natural log 2 over 24,110. Then when we multiply by mass at 100,000 years, we're just multiplying by this figure here, 56.4. When we do this as an actual problem WebAssign, you might want to give a little bit more accuracy on this right here, just for the sake of being sure we have the right value. So here's how I'd actually calculate it in the calculator. So in a calculator like this one, you can say take this value, negative, oh, let me try again. There we go, negative natural log 2, divide by 24,110, then just immediately go times, and I want to multiply by that number. So let's go 56.4197. Let me make sure I get those digits in right. 56.41, there we go, 97. So I'm going to get slightly more accuracy than what's being written here and here on paper. And it comes out at negative 0.0016. Let me take a look at the rounding. I think the rounding here should have really said round to 4. decimal places. Let's just do a really fast edit on that one. 4 decimal places makes a little bit more sense because in this problem, after 100,000 years have gone by, sure, you have 56.4 grams, but the decay rate is still with a half-life of 24,110 years. So at time 100,000 years, we're only losing 10 thousandths of a gram per year. Because of the negative sign, it's telling us we have things that are shrinking or decaying, not growing. Any questions, folks, with our conclusion there in part C? Okay, well, so far, these are the major kind of things that you're going to see on, say, a real exam question or a quiz problem. A lot of the problems I'm going to ask have really fast setup, like in part A that we saw in this problem. And I think the most trickiest thing about all these questions is watch out for anything that asks you about a rate of change. That's when a derivative comes into play, but you're not differentiating the original function here. You're just citing this formula, whatever form it takes. It could be dp dt, it could be dm dt, like we're calculating right now. But it's always k times the population size or the amount of mass. So I think that's what makes these kind of problems a little bit tricky. And with what we have going on with where we're at in class, looks like we maybe have time for just one more part. We'll finish out part D. For the brave, I think you could start this section WebAssign through section 3.6. But I have one question in there that's similar to example 4, which is a little bit trickier. So if you want to wait before you jump into 3.6, I think that'd be totally reasonable. We'll finish off these notes when we come back on Wednesday's class. So let's make our part D here, our last one for the day. I think we might be able to finish this in one spot, but let's go down a page just for good measure. We're also going to need definitely the model right here, so we'll take a temporary screenshot. So here's the situation so far. We know that after 100,000 years, a very long time, our initial mass of 1,000 grams has only disintegrated to 56.4 grams. So now a natural question might be, if you ever had 1,000 grams of this plutonium in your garage, how long for there to be just 1 gram remaining in the sample? Well, that's kind of a tough thing to estimate, I'd say. So let's calculate it exactly. We want to know when time t is the mass at time t equal to just 1 gram. These kind of questions always go essentially the same exact way. We write out an equation from the given information, then we do a massive substitution right here. In place of mass at time t, we're just throwing in that entire function we put in at step 1 or part A. So 1,000 e to the negative t, natural log 2, divided by 24,110 equals 1 gram. Let me just double check I got it all in there. Okay, so I think that's our model. And same exact steps as before. We first divide by 1,000, then we'll take the natural log of both sides. So on step 1, we've divided on 1,000 on the left-hand side. So it's now just e negative t. Natural log 2 divided by 24,110 is equal to 0.001 1,000th. Then take the natural log of both sides of this equation. Again, for the notes, I usually write out this step just to show logically what happened on the next line. So natural log e negative t, natural log 2, divided by 24,110 is equal to the natural log of 0.001. Logarithms are kind of tricky. When you look at that right-hand side, it looks like we're visualizing a positive number, but we're really not. The reason is y equals natural log x has this shape. It intersects right at 1, and so if you put in something less than 1, you're way down here on the negative end of the x-axis, or excuse me, of the y-axis. So in other words, natural log 0.001 is truly a negative number. That's actually really just because that can sometimes be kind of confusing in the middle of our steps. So we've got a cancellation going this way. It's now negative t natural log 2 divided by 24,110 is natural log 0.001. Last step to finish out this whole problem is just to multiply by the reciprocal of this constant, including the negative sign. So we get t equals negative 24,110 divided by the natural log of 2, multiplied by the natural log of 0.001. And notice at this step, our answer could look like it's totally wrong. I've done exams where people saw this and they kind of just deleted everything on their exam because they felt like they were on the wrong track, is what I imagine. But this is really a positive number because that's negative, and so is that one right there. It just doesn't look like it the way we write it on paper. So here's our last step. Shove all of that into the calculator, and here's what we're going to get. They get 24,110 divided by natural log 2, multiplied by the natural log of 0.001. Gives us this many years, 240,275.1 after rounding. I already forgot the digits, 240,275.1 years. On this problem, if you didn't round it accurately on a real exam or quiz, I'm okay with that because 240,275 years is a really long time. It won't make a bit of difference if we got the rounding a little bit off right there. But we did it, folks. That's how much time it takes for plutonium of that isotope to disintegrate to just 1 gram from 1,000. Any questions at all getting through this process? Okay, well, we have a few minutes on the table, but I don't think breaking into another problem that takes at least 12 minutes or so is a great idea. So we'll come back to that one on Wednesday, kind of review how all this goes and see how to get through that problem. Then what else we have going on Wednesday is we're going to begin our work in derivatives of logarithmic functions. It's a little bit tricky if you're rusty on logarithms. So you can look at the logarithms review material document. We'll be pulling this up as we do the problems, mostly looking at this end right here, properties of logarithms. But to make the class a little bit smoother, before Wednesday's class, if you feel rusty on logarithms, take a look at this right here, logarithms worksheet. It's just a kind of a crash course to help you get through these kinds of properties of logarithms and see how they go. It's got questions with answers at the very back. So this will be our stopping point for today, folks. I'll see you all on Wednesday. And if you do have additional questions, I'll be back on office hours right at 3:30. But have a great afternoon, folks. See you all later.